Oh, Bill too, sorry.
Okay, so the first part, you guys see what it says? Reading guide part 1. So it's on your packet actually. So actually, no, I lied. It's the like single sheet that's front back. Single sheet that's front back. So it says reading guide part 1, physical properties. Reading guide part 2, properties of solids, and then there's a part 4 and 5. I'm sorry, I missed part 3. Basically today, yesterday I tried to get you started, and then you're going to finish the reading guide today, because I didn't want to make you watch 45 minutes of notes yesterday for homework. Okay, so you're going to watch the rest of them first, and then we're going to come together and we're going to do some of these on the bottom, which is intermolecular forces, interparticle forces, and a little bit more about metallic bonding. So we're actually piggybacking off of the unknowns lab that we did a couple days ago, taking some of that information into this unit. Then after that, we're jumping into solutions. So the types of intermolecular interparticle forces are going to help us understand why solutions work the way they do. With solutions, there's lots of things. There's colligative properties, vapor pressure lowering, boiling point elevation, freezing point depression, solute-solvent interactions, Mentos and Coke. I think what else. But we actually know a lot of the stuff we're coming into. So this part will move kind of rapidly because we have a lot of background knowledge. There are 2 NSMI readings for this one. The first one is liquid solids and solution, or liquids and solids. That's on homework for tonight. But the notes you take today, if they're thorough, then you don't need to do a whole lot there. Kind of skim for the things that we didn't do in the notes. The next one is called solutions, because that's it. Okay. So I have everything in the packet for you. The lab we're doing on Wednesday when I get back is this evaporation lab. Okay, you know, on Monday I won't be here. On Tuesday, nobody will be here. Right? Don't come to school Tuesday. Yeah. So, and I have your lab notebooks I'll give you back. But you guys actually take 3 minutes, draw IMFs with examples. Draw IMFs with examples right now so I can come around and see your notes from the video. I want you to think of a compound that would undergo hydrogen bonding dipole ionization and draw it the way that you would anticipate it interacting. So the quicker we can now get started, then I think you guys will get a lot of your content, except for this. You have to try to fix the concepts in class. So drawing those 3 IMFs. So what do you try from hydrogen bonding?
Water.
Water, like easiest, right? So how do you draw the hydrogen bonding then?
H bonded to an O with 2 lone pairs bonded to another H.
But is that the hydrogen bonding?
No, I mean,
So in order to draw this, you have to draw 2 molecules. First point, do you understand that? Intermolecular, inter means between 2 molecules. You cannot think of it as a covalent bond because a covalent bond is a true bond. A hydrogen bond is not a true bond. I'd rather call it hydrogen attraction, but you know, I'm just a lowly teacher, not the people who make up chemistry terms. So hydrogen bonding is a good example. Water is a good example to use for hydrogen bonding, but you must think of them in terms of their partial positives and partial negatives. Where's the partial positive on the first water molecule? On the hydrogen, okay? This is the partial positive, this is the partial negative. It's like an attraction of between two different charges. They're not full charges though, they're partial charges, and that's what we draw the little S thing for. This is the partial negative, this is the partial positive. How do you actually draw the hydrogen bond? Dashes, right. So not a line, don't draw it as a line, draw it as a like dash like this, or between the hydrogen and oxygen really. But this right here is the hydrogen bond. It's not a true bond. Question?
Yeah. Why wouldn't the two lone pairs go opposite sides?
So if you draw them on opposite sides, you're going to think of it as a linear structure. But we know that water does not. Okay, so there are 4 electron domains there. The 4 electron domains forms a tetrahedral electron geometry. The tetrahedral electron geometry has things like this, one on the back, one on the side. There's no such thing as like opposite sides of it because they all have a 109.5 degree angle between them. So think of it taking on thinking it of a tetrahedron would allow you to see that there's going to be 2 H's like this and then 2 lone pairs like this, or this, or this. But they're never opposite of each other. Cool. So what's another example that you could use for hydrogen bonding? YHF. Okay, so if you did not watch the video thoroughly, then you don't know this. H bonded to F, O, or N. It's the only time that a molecule will be able to undergo hydrogen bonding because it's an extreme case of electronegativity differences that makes these partial positives and partial negatives very, very polar. Not just very polar, but very, very polar. So there's a dipole moment pointing from hydrogen to oxygen, which creates this more significant partial negative and partial positive because of the electronegativity differences between H and O. The same electronegativity difference occurs with H and F and H and N. Why? Why? Right, like look guys, the most electronegative elements on the board are F, O, or N. So there. So all these other things over here, I didn't actually touch it, I'm really close. But all those other ones are less electronegative, so they're just going to undergo dipole attractions, not hydrogen bonding attractions. So, separate example, dipole.
Carbon tetrafluoride.
Lies.
No. NH3.
No, hydrogen bonding. That's N and H. I said a separate example for dipole.
What type of that is?
NH3 would be hydrogen bonding.
Oh.
Right? NH3 would be, so ammonia would be hydrogen bonding because it's H to N. Okay, anybody else other than these people? NF3, nitrogen trifluoride. Okay, so drawing that, we have, what's the shape of this, guys? I don't have to finish it. You should be able to visualize this. Trigonal pyramidal. Trigonal pyramidal. You should be able to think of these very quickly. That's why, I mean, I took the multiple choice, you guys are taking the multiple choice yesterday. It took me about 20, 25 minutes. So some of you guys cannot visualize these because you've not drawn them enough. You've got to force yourself to draw them enough so you're comfortable with them. Let's pretend to draw that everywhere, okay? So these are your 2 molecules. What's attracting? Where's the biggest partial negative on the molecule? On this lone pair right here. There's a big partial negative here. And I'm actually really trying to show you that these partials are bigger, so I'm drawing my little partials as a bigger sign or bigger letter. These are smaller, and this is not necessarily partially positive because of the lone pairs. I know it's somewhat distracting, but they're less negative than the single lone pair on the nitrogen because it has its own space at the top of the pyramid. These are kind of all spread out, so I'm going to call this kind of partially positive. Partially positive. Okay, so we do have a net dipole moment pointing from the bottom to the top. The bottom to the top. Sometimes they just draw it straight through the structure. So then where are the attractions? Slight attractions between what and what? Okay, so between the lone pair on the nitrogen to the bottom of the pyramid on the other one. And that right there is dipole-dipole attraction, which is stronger. Hydrogen bonding. So can you tell me what state of matter might be present, or what might the differences in the states of matter be between these? So possibly liquid, which we're like, duh, water at room temperature is liquid. It has a stronger attraction for itself, which makes the surface tension high, makes the cohesion high, blah, blah, blah. This one may or may not be liquid. It's more likely to be gas and water, though, because the attractions between the molecules are going to allow it to separate. When they separate, what kind of change is that? Physical or chemical change? Because what's not happening?
The substance is not being changed.
Right, the substance is literally taking this NH or NF3 separate from this NF3. Are the bonds internally breaking? No, so it's a physical process because it's a phase change, going from liquid to gas or whatnot. It's not a chemical change because the chemical composition of the nitrogen trifluoride is the same. Okay, so then London dispersion. Give me an example.
Nitrogen.
What?
What?
Carbon tetrafluoride and
Nitrogen. Dinitrogen.
so just nitrogen gas.
Diatomic.
Just call it nitrogen gas. Okay. You can say diatomic, but whatever you just said with the di. Okay, so you can do nitrogen to nitrogen. So here's nitrogen and here's nitrogen. And then carbon tetrafluoride. I'm just going to draw it as CF4. CF4. We know the structure is what? It's tetrahedral, evenly spread out. Is it polar or nonpolar? Nonpolar. I drew these with the partials. Are these polar or are these nonpolar? These are definitely polar. So polar molecules can undergo IMFs of hydrogen bonding or London dispersion. Hydrogen bondings are specific, so they have a bigger partial. These are what? Polar or nonpolar? These are all nonpolar. So nonpolar is going to be interacting through London dispersion forces, and the London dispersion is going to occur between what? Between everything, right? There is no partial negative, partial positive. It's a quick temporary dipole that's created by an electron jumping in the electron cloud to one side to create a really, really, really temporary partial negative. And this side has a temporary partial positive. Temporary, and drawing them very small, and I'm just going to kind of go like this to say there's electron motion. The electron motion is causing this very quick temporary unequal distribution. Well, it triggers a response on this one because if this is partially negative, it's going to create a partial what on this side? Really quickly, right? And these are small. And so for that instantaneous for the instant, there's going to be a quick attraction here. And then it breaks. Okay, and then it's going to do it again. And then it goes away. And comes and goes away constantly. Well, there's the same thing happening here. But which of these has a stronger London dispersion force? In nitrogen or carbon tetrafluoride? Why? Not the trait we look for. The first thing we look for is differences in electrons. This one overall has more electrons. How many electrons does this one have versus this one? You can go with valence electrons, that's fine. How many valence electrons does nitrogen have?
32 CF4.
What?
No,
Nitrogen.
No, it's
10. 5 plus 5 is 10. So nitrogen has 5 plus 5.
Yeah,
Okay, sorry, you scared me. So 28 plus 4 is 32. So there's 32 valence electrons on this one. So the carbon tetrafluoride has more electrons to bounce around to create those partials, right? With me? More electrons to bounce around to create partials means that maybe the partials are a little bit bigger, and if you have a bigger partial difference, meaning partial negative, partial positive, your strength of the London dispersion force will be stronger. So who has a higher boiling point? Nitrogen or carbon tetrafluoride? Why? Okay, I just want to point out one thing. I watch this, I go to these webinars all the time, on my computer. Go to the webinars that AP Chem offers. And one of the guys was like, if your students say break bonds in a IMF example, you get no credit. Even if you are explaining it correctly, do not say break bonds. Thank you, Han, for prompting me because I would have forgot to say that. You can say overcome IMFs. Okay, best phrase to say, overcome IMFs. Write it down, burn it in your brain. Huh? You can say IMFs if you make a little key at the top. So if you make an abbreviation in the exam, you have to define it. And if you plan on using IMF more than once, then please define it. Because if not, if you're writing intermolecular forces, you're using too much time. Okay? So, what? You okay? Thank you. So, if you have London dispersion forces, the higher London dispersion forces occurs with one with more electrons in comparison. That means it's going to have higher physical properties. What are some physical properties we can relate to IMFs now? Boiling point, what else? Melting point, what else? I actually mentioned like 3 or 4. Surface tension, what else? Solubility? Viscosity? What else? Cohesion, so that's going to kind of be more related to surface tension. Yeah. Yeah. You can't measure surface tension. You're just going to say that this thing has higher surface tension than this thing because it's got greater intermolecular forces than this thing. Greater meaning hydrogen bonding.
Conductivity.
No, you can just denote that there is a high amount of surface tension, but you can see it by like a meniscus. So if something has a meniscus like this, then it's got a high amount of cohesion and adhesion, which is a high amount of surface tension. Okay, that's probably good there. In terms of finishing up, reading about physical properties, IMFs, and how they relate, and a little bit more, solids, ionic, metallic, network covalent, and molecular solids, that's what you're watching your videos for. Because it's all, instead of making you read the entire NSMI and take notes. You guys are killing me today. Then you're going to finish your notes from here, okay? So, reading guides, go grab a laptop. I'll show you where everything is. Go grab a laptop. I thought it was your laptop.
Why wouldn't you do mine?
Why would I not think that's it's on your sheet. It's D on part one of your sheet.
I think I got it.
You probably did. Viscosity. Yeah, you're right. I gotta take some stuff off of the website. Ugh. Okay. It's called Reading Guide 1, Reading Guide 2, and 3. I just combined them because some of this is background knowledge. If you want to watch me on 1.5 speed and take good notes, if you don't watch me on 0.5 speed, take good notes. This is personalizing it for yourself. Some of you guys might have more recent memory of honors chem. Some of you guys might have less recent memory. I know you have no memory. You got amnesia from honors chem. But some of this stuff is really easy. Some of this is new. So please take notes so that you don't have to take as many notes on your NSMI. But take notes where you want to, because this specifically is what I want. I want some information on the properties on the reading guides, and then that table filled in. If you want to make this on a separate sheet, that's totally fine. Okay? So, after you get through, I have to figure out which video it is. One of the videos has me going through, oh, dang it. There's me. You know, I'm super goofy on these. My husband laughs at me. I get a little, I said something weird on this part, but you guys will figure it out. But when you get on the next video part, where is that? Picking up where we left off here. Okay, so here's where, you guys see, I actually do the first problem set with you. Do you see the problem set that's labeled A right here? Everybody with me? It says interparticle attractions and properties. I'm doing A with you here, so make sure you're doing that when I do it on the video. Because at the end of class, I want to do B through D with you if possible. Because I would like to do this. All right, you guys got like an hour for 30 minutes of video. Okay? Don't use the hour. Use like 40 minutes so I can do the last bit at the end of class. Okay, I'll leave you alone.